1.3 billion years ago, in a galaxy far, far away, two black holes, each roughly 30 times the mass of our sun and drawn by their immense pull of gravity, spiraled inward towards each other at over half the speed of light. When they collided, the energy of their impact was so great that it created a shockwave that could be heard all across the universe. And this is what it sounded like.
Okay, so that might not be the massive explosion you were expecting. And as you're probably aware, sound doesn't travel through outer space.
We've been lied to our whole life by movies and television.
But that little bitty thump that you did hear was a direct sound translation of the gravitational waves emitted by the collision of two black holes.
And that little thump could signify the beginning of a whole new way of understanding our universe.
Or it could just be the beginning of an EDM song.
Everywhere we go, we're surrounded by waves, and these waves send us information about our world.
Light waves emitted by the sun or artificially bounce off of objects in our environment, telling us about what they're made of, their shape, their size.
Sound waves can tell us about an object's location, and if it's moving, how fast.
And then there's just waves, which are mostly here for visual reference, but they can tell us things like about the weather, or if the tide's coming in, or if I should go wax my surfboard right now.
But the waves we're most interested in today are by far the most difficult ones to detect, and they could be one of the most important scientific discoveries of the past century. On September 14th, 2015, a team of scientists working at the Laser Interferometer Gravitational-Wave Observatory, or LIGO, detected a ripple in the fabric of space-time. This was the first direct proof of gravity waves, but the idea that something like this could exist arose about 100 years earlier.
So Einstein came up with general relativity in 1915, and this was his theory to explain gravity. And Einstein's key insight was you can think about gravity as the curvature of space-time.
This is Daniel Holz. He's a physicist on the LIGO team and a faculty member at the University of Chicago in the Department of Physics.
And the Department of Astronomy and Astrophysics, and the Enrico Fermi Institute, and the Kavli Institute for Cosmological Physics.
Yeah, that sounds like a lot of different institutes.
Yes.
Okay, so Einstein's great revelation was that all matter bends space and time. Gravity is actually just the result of space-time being bent.
The more massive the object, the greater the bend.
His analogy was, you imagine you have a bowling ball, you know, it's heavy, you put it on a trampoline, it bends the trampoline. Now if you take, say, a little marble and you shoot it near the bowling ball, it'll kind of spiral around the bowling ball. And gravity does the same thing. You take the sun is massive, it bends all the space-time around it, and the Earth is now the marble, and the Earth is just kind of going around. It thinks it's going in a straight line, but because the space-time is curved, it goes around and around in an orbit. So gravity is pulling us down, but if something changes, suppose the Earth were to move, then the gravity has to change. The theory of gravity says those changes are kind of propagated out through gravitational waves.
Essentially, gravity waves work like any other kind of wave. Picture what happens when an object falls into a pool of water. Waves are created at the point of impact and propagate outward. The waves will continue to travel, and you can sort of get a sense of the size of the object by the size of the waves. Gravity waves work the same way, except instead of ripples through water, they're ripples through space-time.
And any object, no matter how massive, will make waves if it's moving around.
So for example, right now I have some mass and I'm pulling on the rest of the universe. Not very much, because I don't weigh that much, but I'm pulling. And if I were to get up and run across the room, then I would be pulling in a slightly different direction. And gravitational waves go out to the rest of the universe to say I've moved.
Even though we're surrounded by gravity waves, they're extremely subtle, so our best chance to detect them is to look for waves created by the most massive cosmic events possible, like supernova and collisions between neutron stars and black holes. So how does one go about detecting gravitational waves?
They're very, very hard to detect. They're very, very weak, and so we need an extremely sensitive instrument. And in fact, we had to build what's the most sensitive instrument ever built. In some sense, the most sensitive ruler, the most precise ruler that's ever been built by Farr to detect them. And that's what we've done over the last 20 years or so.
This super precise ruler that Daniel is referring to is known as LIGO. LIGO is comprised of two separate detectors, one in Hanford, Washington, and one in Livingston, Louisiana. Each detector has two 4-kilometer-long arms that extend out from the main facility perpendicular to each other. Inside each of these arms is a laser beam that bounces back and forth and can measure slight changes in distance, which is basically what you need to do to detect a gravity wave.
So if a wave were coming through us right now, then what it does is it changes the distance between us by just a little bit. We get a little closer, then a little farther apart, and closer, farther apart, and it just oscillates like that. And right now, waves are passing through in every which way all the time. We know that. They're happening.
Okay, I don't feel anything.
You don't feel anything. The waves are very small, so the changes in distance are very, very slight. Now, you really want to measure two distances. The sort of pattern you're looking for that tells you, yes, this is a gravitational wave, distance between us, and then the distance between me and some other object over here. And I want the distance to that object to get shorter when the distance between us gets longer, and then for those to oscillate back and forth.
So when a gravity wave passes through LIGO, it will compress and expand the space around LIGO and LIGO itself, making one of the laser arms slightly shorter while the other arm gets slightly longer.
Where slight is not just, microscopic, it's way smaller than the smallest thing you can normally think about. It's way smaller than, a hair or an atom or a proton. It's tiny, tiny fractions on this distance. It's a tiny fraction of a proton.
Like what fraction? What are we talking here?
So on 4 kilometers, which is the size of the detectors we've built, it's about 1/1000th of a proton.
1/1000th of a proton.
So for something 4 kilometers away, that's the amount of change in distance you're talking about, which is really tiny.
That's insane.
1,000th of a proton. That's like changing the distance between us and the next closest star outside of our solar system by the width of one human hair.
So not much,
Right.
basically.
Very tiny.
It's kind of hard to wrap my mind around this because so we're talking about a laser beam that's 4 kilometers long. You're looking for a change that's 1,000th of a width of a proton.
Yeah.
I mean, couldn't like a squirrel or somebody sneezing cause a change like that? How do you tell it's a gravity
Absolutely.
wave?
What it takes is building this incredibly sensitive instrument and then ruling out all these. You want to isolate all these other things. It's just as you said, if a squirrel walks by, you can notice that, and that's a problem. If a cloud goes over the detector, you notice that. If there are waves crashing on the coast far, far away, you notice that. Anything, you notice, anything that happens. So you have to control all of those things very, very carefully.
Even though LIGO was built in the mid-90s, it wasn't until 2010 that the system underwent crucial upgrades to get it to the sensitivity needed to detect gravity waves. 5 years and over $600 million later, advanced LIGO was powered on for the first time.
In the last few years, we've gotten much better at isolating the Earth, basically, everything that has to do with motion of the Earth. But there's one thing which I've not mentioned, which is crucial to this, which is we have 2 detectors. We have one in Hanford, Washington, and one in Livingston, Louisiana. And we want the pattern, this alternating pattern, to happen in both detectors essentially simultaneously. So if a squirrel is going through one detector and causing some sort of pattern, some oscillation, chances are that at that very same moment there isn't a squirrel going in the other detector. And then when we finally, which we did in September, see something which does the exact same wiggles in both detectors at the right travel time, then you say, oh, that's real.
So someone in Washington calls up someone in Louisiana like, hey, we got a wiggle. You guys have a wiggle?
Exactly. That's basically what, the computer does it, but that's basically what we're doing.
And on September 14th, 2015, 2 days after advanced LIGO was powered on for the first time, the 2 detectors noticed a wiggle. The nearly simultaneous and identical patterns fit Einstein's prediction perfectly and couldn't be explained by anything other than a gravity wave. So was that the most exciting thing ever for you?
Yeah, most exciting thing ever by far. It was totally incredible to turn on the detectors and there it is. And it wasn't kind of marginal, well, we're not sure. It was like, oh no, this is definitely exactly what we predicted. It's this beautiful waveform. It's amazing. It was amazing. It's still amazing. I still can't, you look at it, you just can't believe, there it is. It's just what we predicted. Yeah. It took over a decade to convince the rest of the physics community, let's build this. This will really be cool if we can get it to work. And this is one of these cases. It's a government agency. It's the National Science Foundation said, we think it's worth doing and spend hundreds of millions of dollars on it. even though some people said it'll never work, and even if it does work, maybe you won't detect anything. And they just went and pushed, improved the technology, and then finally built this advanced detector, turned it on, and then 2 days later had this, one of the most amazing discoveries, I think, in physics of the last 50 or 100 years, just like that.
Okay, so about 100 years ago, Einstein theorizes gravitational waves and a bunch of other stuff. And so now they've been discovered, but what's the big deal? Like, why is that so significant?
Okay, so I think there are a number of things that make this important. What we've detected is perfectly described by general relativity. And the fact that that's true, I find quite remarkable. But I think the thing that has people most excited, within the community, I think the thing that really grabs us is this is just the very first event. This is just the first thing we've happened to detect with this new technology, this new way of probing the universe. The comparison that's usually made is it's with Galileo. Galileo pointed, his telescope. Okay, there's some moons going around Jupiter. That's really interesting. But that kind of turned into our whole notion of the universe. It has a finite age. All these things we've learned about the universe comes from that very simple first detection. And we've now done the equivalent. It's not an optical telescope, this is now gravitational waves, but it's opening up this whole new way to learn about the universe. The analogy we make there is we're familiar with seeing, and we've seen the universe, and we have all these telescopes, and now we have a way to listen to the universe. Gravitational waves are in some ways like listening to the universe. Now, just to be 100% clear, this is not sound. Sound is something that happens through air, but the truth is, part of the reason we use this terminology is because if you take the actual waveform from these systems and you just take it and you put it into your speakers and turn up the volume, you can hear it with the human ear. When a gravitational wave is generated from the very heart, right by the surface of the black holes, they now propagate through the entire rest of the universe. No matter what's there, it goes right through it and right to you, because they don't interact with anything. Right. So it's very hard to block.
So there's essentially, like, in some ways, no limit to how far away these waves can be emitted.
So for example, taking that to the natural extreme, there's the Big Bang.
Right.
The Big Bang,
Heard of that.
there was a lot going on in the Big Bang. We expect gravitational waves to have been generated. Those gravitational waves, once they're generated, will travel without being changed at all throughout the universe. So if we could detect those, we're detecting exactly the waves that were emitted from the Big Bang. The power to do that, there's no other way to probe that early in the universe. We have some ideas of some of the things we might hear, like black holes crashing into each other, but there are probably things we haven't thought of that are happening out in the universe, and we're going to start to hear them. And so it's the sort of unknown unknowns that are most exciting. We just have no idea. No one's ever been able to do this before. So now we have this machine, and this summer we're going to turn on again, and we'll be the first ones to know what the universe is saying. I mean, it's really, so that's, I think, the most exciting part is this sort of unknown future.
For thousands of years, human beings have been looking into outer space, but now, for the very first time, we can finally listen to it.
And if we listen real close, we'll be able to explore the depths of the universe further than we ever thought possible. Hey, thanks for watching. Liking and subscribing is something that we like and subscribe to.
That's right, Craig. Also, big thanks to all of our Kickstarter supporters for making the summer season possible. And as always, if you want, you could support us on Patreon by going to that link over there. So what do you guys think? Are you excited about gravity waves? What do you think they'll be able to tell us about our universe?
Are you excited about waves in general? Can you surf? I can't. By the way, this is Ryan.
Hi.
He's just gonna host a few shows this summer, and he really likes physics. So
I really like physics. I'm not like replacing Matt or anything.
Matt's still alive.
Yeah. He'll be back.
Yeah. Not only do I like physics, I live physics.
That's true.
Like, I experience it.
That is very true.
Last week we tasted some beers and talked to the guy who started the Cicerone program, and you had some things to say about it. So I'm not familiar with Korean, so I can't pronounce this person's name, but they're asking about what is a good tasting beer. There really is no good tasting beer. It's obviously a matter of opinion, and that issue is kind of complicated when you consider all the kinds of flavors of beer, especially nowadays. There's saisons and sours and bitters and sweet. It really comes down to what you like. Being a cicerone isn't necessarily telling you what is a good beer. It's educating you about flavors and about how to present a beer to a customer, about the proper ways of maintaining a beer. Personally, for a good beer for me, it depends on my mood. I often like wheat or saison beers. Sometimes I like a good refreshing Pilsner on a hot day. Like right now, hand me a beer. We don't have beer right now. It's morning.
Sounds really good. GM Dill, Colin Sturks, and a number of you said that Belgium is the best place in the world for beer. Personally, I really like Belgian beer, and I would love to fly to Belgium and find out if that's true, maybe in a follow-up video.
Doug Townsend took issue with us complaining about there being too many IPAs. We're not saying IPA is a bad beer. In fact, I like a lot of IPAs. I'm just a little sick of them because they're everywhere and I've drank them a lot. I think the point Ray was making is that it's so oversaturated that people are missing out on all sorts of other flavors of beer. That doesn't mean you shouldn't like IPAs. In fact,
yeah, IPA would be my favorite style of beer, personally. I love the hoppiness and the bitterness of IPAs. Yeah. I find them refreshing and delicious.
Yeah.
But I can see what you're saying, so I get it.
IPAs are IPA okay.
Daxter commented that Ray reminded them of J.K. Simmons. Personally, I don't agree.
J.K.
Simmons.
Thank you for watching. Next week we have a video all about a light bulb that's been burning for a long, long, long time.
Whoa. How long are we talking?
3 longs.
What, 3 longs?
Yeah, over 100 years, I believe.
Oh, okay.
Yeah.
So long is about 30 years then, basically. It was like 33 years.
Yeah, look it up. That's the technical definition of long.
Okay.